In this section of Chapter 13, we're going to be looking at our oxymercuration reactions. So the first reaction is going to be the hydration of an alkene through the oxymercuration reduction reaction, oftentimes referred to as an oxymercuration demercuration reaction. So what we're going to be doing with these is we're going to be using the mercury 2 ion to help us run the reaction. So instead of using a halogen as our initial electrophile, we'll be using mercury as our initial electrophile. So this allows us to create alcohols without having the halogen present. So we're going to be adding mercury 2 acetate and water in THF to our alkene. We're then going to treat that system with sodium borohydride to produce the final alcohol. So we're still going to end up getting the Markovnikov product. The water, the second nucleophile, will still come in and attack the more substituted carbon atom. But what we're going to see with this type of reaction to produce the alcohol is we're not going to see any carbocation intermediates because we'll be producing the merconium ion intermediate. That will also allow us then to produce one product instead of seeing carbocation rearrangements like we've seen in previous chapters when we were generating alcohols through the use of the alkoxide anion or through the use of just water and base or under acidic conditions. So with this reaction, we have our alkene and we're going to put it in the presence of our mercury 2 acetate. So remember that OAC stands for that acetate unit for us. We will still have water and THF. THF here is just a solvent for us. It's a non-protic solvent. So initially through this reaction, we end up generating the alcohol on our alkene, but we also still have the mercury acetate associated with the alkene as well, because we'll go through this merconium ion. The second portion of this reaction is then using that sodium borohydride, which is a hydride species. It's a reducing species for us. And this basically gets rid of the mercury. It reduces the mercury away and generates that to be a carbon-hydrogen bond. So we no longer have the halide associated with our compound, and we just generate the alcohol from the alkene. But we have not used strong acidic conditions, nor do we have to worry about any type of carbocation arrangement like we have seen in previous chapters. So let's look at the mechanism associated with our reaction. So we have the alkene. We are also going to have our mercury acetate. So mercury is going to be associated with 2 acetate ions. And mercury being a transition metal, it has d electrons associated with it. So it still has some electron density around it that is not being utilized in bonding or in charge distribution. So our nucleophile will come in and attack the metal that still has vacant orbitals associated with it. And those extra electrons that are on the mercury will also come in and attack one of the carbons from the alkene as well. Through this process, we are also going to break the bond between one of the mercury species and one of the acetate ion species as well. So what this ends up generating for us is going to be the merconium ion. So you'll notice that we have mercury. It has 3 bonds associated with it, and it also has a positive 1 charge. So this is our merconium ion. So it's a very similar species to what we saw with the chloronium and the bromonium ion. We have also then produced again the acetate anion. But then we also have water in our reaction flask as well. And again, for the same rationale that we saw previously, it will be the water that will behave as the nucleophile and come in and attack the merconium ion. Again, we're producing the Markovnikov product, so the water is going to come in and attack the more substituted side for us. At the same time that happens, the bond between that carbon and the mercury will break as well. So now from here, we still have a protonated alcohol species because we added water. So we will need to come in and deprotonate. So typically our water will deprotonate it for us so that we end up getting that initial compound that we looked at, which is the alcohol, as well as having the mercury on our alkene as well. So from here, this is where we now bring in our sodium borohydride, and it does a reduction for us. We are not going to discuss reduction reaction specifics right now. We will leave that reduction specifics to 202 chemistry. So right now, you just need to know what happens in terms of a product. So this sodium borohydride is going to reduce away the mercury species and replace it with a hydrogen, so that we generate an alcohol that is a Markovnikov alcohol. So again, you do not need to know the mechanistic aspects of reduction right now. You just need to be able to know what reduction does, and that is it's going to replace that mercury with a hydrogen, so it will reduce the compound. We are also going to see the same type of reaction, this oxymercuration hydration of an alkyne. We're still going to be using the same mercury 2 catalyst and water, but this time instead of producing an alcohol, it will be producing a ketone. This is once again going to go through the keto-enol tautomerization. We'll initially generate the alcohol, but the alcohol will be on a double bound carbon, so an sp2 hybridized carbon atom, which will then tautomerize into the ketone. One of the things that you will notice is that we no longer need to use sodium borohydride to reduce the mercury away. Because of the tautomerization, there will be no sodium borohydride required. There will be no reduction required as we go through this reaction. So if we look at our reaction, we have the alkyne, we will have water, we will have our mercury 2 acetate. And with this process, we will end up producing the ketone, like we have seen before through the keto-enol tautomerization. One of the things that we do have to be careful about is, again, I have showed the reaction as a terminal alkyne, which will give us the ketone with a methyl group as one of our groups. If we have internal alkynes, we will end up getting a mixture of ketones once everything is said and done, because we no longer have a more substituted side. We no longer have a Markovnikov product for that second nucleophile to come in and attack, because both of the carbon atoms now have the same substitution. So we can have our internal alkyne reacting with our water. I'm going to use a different mercury 2 catalyst here, so it just needs to be a mercury 2 ion with the alkyne. It does not need to be mercury 2 acetate. So we could also see utilized with alkyne reactions something like mercury 2 chloride. We'll see something very similar in terms of the zirconium ion intermediates and the reactions that we're going to be dealing with. But since this is an internal alkyne, we can see a variety of different ketones being produced depending on where the water adds. So this ketone here would be that the water is adding to the carbon on the left-hand side of the triple bond. But we will also see the product where the water adds to the carbon on the right-hand side of the triple bond. So we will get out this mixture of products because there is no longer a Markovnikov product, since both carbons have the same degree of substitution.